Alright, so in this video I'm going to be talking about another article about few-shot learning, and the task is about intent classification. But we do it with slot filling and with retrieved examples. So I'm going to be focusing on this paper in 2021. Few-shot learning arises in important practical scenarios such as when a natural language understanding system needs to learn new semantic labels for an emerging, resource-scarce domain. In this paper, we explore retrieval-based methods for intent classification and slot filling tasks in few-shot settings. Retrieval-based methods make predictions based on labeled examples in the retrieved index that are similar to the input, and thus can adapt to new domains simply by changing the index without having to retrain the model. However, it is non-trivial to apply such methods on tasks with complex label space like slot filling. To this end, we propose a span-level retrieved method that learns similar contextualized representations for spans with the same label via a novel batch softmax objective. At inference time, we use the labels of the retrieved spans to construct the final structure with the highest agreed score. Few-shot learning is challenging due to imbalance of the amount of data between the source and target domains. We focus on retrieve-based methods, which maintain an explicit retrieval index of labeled examples. The most basic setting of retrieve-based model for few-shot learning is, after training a similarity model and encoding target domain data into index, we can retrieve examples most similar to the given input, and then make a prediction based on their labels. So we have a query, CLS token, and then I'd like to book a table. So these are examples in the support set. For each span in the input space, we retrieve its most similar span from the retrieved index. I don't think in human brain we do this thing. In human brain we have different systems, and the separation of concerns is very serious. So each of these modules only do one task, and only one task. But they share their things so that it's like a microservice. Each one is on a focused domain, and just they pass in a, like if it is a Kafka, they pass in something in the middle. So let's carry on this paper. There is benefits for using this retrieval, this paper, because more compared to classification or prototypical networks, which I really like, which require adding arbitrary number of instances to the training data, a retriever, this concept can guarantee the prediction when a similar query is encountered. At the same time, by the way, one of the drawbacks of few-shot learning is that in real world, they don't give you an episode so that this is a query for the final testing, and you should retrieve those data that are relevant, and you expect that your classes is one of those few prototypes. So retrieval can be augmented with the classical few-shot learning so that it becomes more natural and realistic, pragmatic work of few-shot learning. So we consider two tasks where the input is an utterance with tokens and the output is some structure. For this slot filling task, the output is a set of non-overlapping label spans where R sub I is a span of X. And you know about this slot filling task and intent classification. So the retriever is the only trainable component in our model. So given a query span from the input X, the retriever returns a set of labeled spans with the highest similarity score. So retriever in this paper is different from what I was talking about. Of course, not totally different, but they mean that they just retrieve a set of labeled spans. Because the combinatorics is huge, so they retrieve something that is more relevant. And they find a similarity score. And then for each query span, we compute a similarity score against all other spans. So it's very artificial. Human brain is not like this. We don't artificially do these things in our neural networks of our brains. It's very artificial. It's very structured. Structure is created human brain differently. So we experiment with 3 reduction functions. These 3 reduction functions. The mean reduction averages embedding of the spans with the same label and is equivalent to prototypical networks similar to hard negative sampling to increase margins among classes. Max takes the most similar span to the query as the label representation, while min-max takes the least similar span when considering spans with the same label as the query. And after training, we build a dense retrieval index, where each entry is indexed by Z, and the entries come from examples in the support set. So we have 2 tasks: intent classification and slot filling. So once we get the candidate spans with similarity scores, we use beam search to decode a set of spans. Another thing that is not relevant to human brain is this beam search algorithm. It's very artificial. Our human brain does not do such things. So we should replace it with better paradigms. And beam search can avoid suboptimal decisions that a greedy algorithm would make. And they do use for clinic intent classification dataset. And this is the comparison on this dataset.